Okay, welcome back. Sorry, I'm a little bit late. I thought I had uploaded um, the lecture slides, and apparently I have not. So I've been trying to upload the slides. Let me share my screen so you see what I'm doing. Um, I'm about to push the slides up to the server. Oh, I already did that. And now I need to update the class webpage. What's kind of sad, maybe, is that I do teach a web programming class, and there I teach all kinds of fancy things you can do, all the fancy packages you can use to develop your website. And here you can see that what I do is I actually go in here and edit HTML directly. Okay, so this is what I need to push up for you. What I have here is in a slightly different order than I actually taught the class. So I have to move things around just a little bit. Okay, so, all right, so today is not November 19th, but April 29th. And okay, we get rid of this. This is from last semester. Comment that out. This is like programming in assembly language, and then link to today's slides, which is the 29th. Okay, I believe I have that. Let me make sure that that looks right. Okay, so slides.
Wait, Professor, you programmed your own website?
Pardon me?
You programmed your own website?
Yes, I do.
Nice.
Yep, that's what you're seeing. You're seeing how the sausage is being made. All right, so now I'm going to actually upload all this stuff. I do teach the web programming class, and believe me, this is not what I teach. I actually show people how to use jQuery and React and all those nice packages. And then, of course, I myself don't use them. It's like the shoemaker whose kids don't wear shoes. So, okay, so.
Yeah, but your website's going to be compatible with older browsers, and it's going to load a lot faster on slower connections.
Yes, that is true.
All that extra bloat and non-free JavaScript.
Okay, so hey, good excuse. Okay, next time somebody points that out to me, that why are you using HTML directly, I will say that's because I want it to load fast. Okay, well, let's see if I manage to get it all to work. Okay, so this is going to do, let's do a refresh. Okay, hang on. You probably don't see this, but Zoom puts all these controls on my screen and they get in the way. Okay, so let me make sure that the stuff actually. Okay, this is what we got here. All right, there's today. Okay, the slide. Okay, slides are there. This test program is there. And the other one, I assume, will also be there. These are two programs we're going to look at today. Okay, yeah, sorry about that. Somebody wants to send me chat messages. Okay. All right. Okay, let's get going. Okay, so here is a project schedule. So that's going to start. These talks are going to start next Thursday, a week. I should have put on the slide again what I expect these presentations, about 10 minutes each. So they're very short presentations. And I want you to describe the language that your project is going to use. What source language are you compiling? Maybe say a few words about it. Why did you choose that language? And if you invented your own language, then maybe say a few words about what's new and exciting that you did. Show us your grammar file. And I don't want you to go over it line by line, but point out some highlights. You can show us some syntax diagrams if that's easier. Show us some sample programs you've written in your language, and point out the features of your language, whether it's a subset of an interesting language, then just say what subset you're using, and show how your sample program makes use of that subset. More exciting is that if you invented your own language, you're going to show us sample programs written in your language, and you can point out what's special about your programs. Show us what kind of code you're going to generate, code templates. You may actually show us some code that you generate, Jasmine code that you generate for some statements. Okay. Now, what's not required is that code actually runs. Okay. It's not fair for me to ask for that, because some of you are going to be presenting a week before others, and so that's not something I can legitimately ask for. Okay, if you can compile and show something running, then that's great, but that's not a requirement. Okay, I am going to put together a short survey that, as each team is presenting, the rest of the class will be rating the project, and I will publish the questions on the survey ahead of time, so you'll know how to prepare for your presentations. Okay, so this is the schedule that I have. Again, if two teams want to trade places, just let me know. Okay. All right, any questions about the project presentations? I'll send out a message, an announcement saying everything that I just said about what you should be doing during the presentations, okay? And they are short. I mean,
Professor?
half-hour presentation or anything. Somebody needs to mute. We're getting some sound.
Oh, I had a question.
Oh, question, yes.
So for the presentation, we don't need to like finish the project. We can just say like what we plan to do.
Yeah. I mean, this is a snapshot of so if you're presenting next Thursday, show us what you have. Yeah, and
Okay.
we're close to the deadline, so you should have something. Yeah,
Right.
This is meant to be a snapshot. This is my sneaky way of making sure that everybody is getting close to finishing the project. So if
so the presentations are required, or they're extra credit?
they're going to be required. I know in the beginning I mentioned that I thought they would be extra credit because there are so many projects, but then I managed to pull the schedule up a bit so that there will be 3 days available for project presentations. And of course, during that time, you're all working on finishing your projects. So it's probably best that I don't give you too much more new material. Okay.
Okay, thank you.
Yeah. Okay. All right. Yeah, I did say in the beginning of the semester that I hadn't decided whether they would be extra credit or required, but since I managed to juggle the schedule a little bit to make extra time, so we're going to do it this way. Okay. All right. So I'm going to continue talking about issues that professional compiler developers are concerned about. For your projects, this is just like background material, but I think it's important that I at least mention these topics. Okay. All right. So grammars. Okay. Now, obviously, you know what a grammar is. It's a description, a very detailed and precise description of the syntax rules of your language. And there are several classifications of grammars. Okay, the kind of grammar that we've been using is known as context-free. Okay, and why is that? Okay, so the production rules in the grammar look like this, right? You have on the left-hand side a single non-terminal symbol, and then on the right-hand side you see what constitutes that non-terminal. So here we're saying that, well, a simple expression is made up of a term plus a term. And of course, later on, you have to define what a term is and so forth, okay? So the way it works then is when the parser is parsing your source program, okay, whenever it sees term plus term, okay, it knows that, oh, term plus term is an expression, a simple expression, okay? And so we can say that, okay, what the parser is doing is reducing term plus term to a simple expression, okay? And so it's doing all these reductions, okay? Now, this reduction is made, well, we say it can, the parser can freely reduce the right-hand side to the left-hand side, regardless of the context, okay? So when it's parsing your program, whenever it sees term plus term, no matter where it is in your program, the grammar says, okay, you can reduce it to a simple expression, okay? That's why it's called context-free, is that these reductions are made regardless of context, okay? All right, so that's, so if we look at possible grammars, okay, well, regular expressions are grammar, okay, and basically they give us the syntax rules for our tokens. Remember, we had what are called regular expressions to say what a number is, what a identifier is, what are the special symbols. Those are the low-level elements of the language, and we can describe them or define them using regular expressions, okay? Yeah, that's where you have the plus sign to mean one or more repetitions, and a star to mean 0 or more repetitions, and then we could say that certain things were optional. Okay, those are all done with regular expressions. That's a very low-level grammar, okay, and we use that to define our tokens, okay? Now, context-free, okay, above that we use a context-free grammar to describe the statements of our language, right? Statements are a little bit more complicated, and we're not able to use a regular expression grammar to define the statements of our language, okay? So we use a context-free grammar, and that's what, when you created your .g files, you were using a context-free grammar, okay? Now, context-free is a subset of context-sensitive, okay? So context-sensitive grammars are more, okay, well, context-free is more powerful than regular, okay? You can define more things with a context-free grammar than you can with a regular grammar. So regular grammar, we're using it just for tokens, okay? And then we have to use a context-free if we also wanted to describe the grammar of statements, okay? And context-free is a subset of context-sensitive. So let's take a look at context-sensitive, okay? All right, context-sensitive, okay, as the name may imply, says you can do reductions, okay? Remember, we said we could reduce term plus term to simple expression regardless of context. Wherever the parser sees term plus term, it's going to say, oh, that's a simple expression, okay? Context-sensitive says, okay, now the grammar rules look like this. So here on the left-hand side, you have more than one. You can have more than one non-terminal symbol, okay? And here, this says that, okay, here is some construct, which I've labeled little b, okay? It says that you can reduce little b to big B only in the context of A and C. Okay, so we're allowed to do this reduction only within this context, okay? Now, how would we use that? Okay, well, for example, let's say we have a rule, okay, and this is for sure a rule that we've seen before. An identifier must have been previously declared to be a variable before it can appear in an expression, right? If you have an identifier in an expression, then you can say, well, you can't use that identifier unless you've already declared that identifier to be a variable, okay? So with a context-sensitive grammar, we can actually capture that rule, okay? So for example, if A is the variable declaration, okay, this says that if you have an identifier, which, okay, here let's say that B is an identifier, you can say that B is really a variable only in the context that you have previously seen the variable declaration, okay? And in this case, C is empty, okay? So here is the context that allows us to reduce an identifier to a variable, okay? The context is that that there had been a previous declaration, okay, of that identifier to be a variable, okay? So you're looking at this and you're thinking, wow, this is pretty powerful. We can actually express more rules with a context-sensitive grammar than we can with a context-free grammar. So why don't we use context-sensitive grammars instead, okay? Well, okay, so I'm just repeating what I said here, that we can reduce an identifier to a variable only in the context of a prior declaration for that identifier, okay? So why aren't we using context-sensitive grammars? It turns out that if you're going to write a parser, yes, question? Okay, if you're going to write a parser based on a context-sensitive grammar, turns out to be a really, really difficult task. Okay, so we're going to say, well, it's really too hard to use a context-sensitive grammar, so let's use context-free. And then to augment the fact that we're using context-free, we're going to have semantic actions, such as having a symbol table to allow us to fully implement the rules. So with a context-free grammar, okay, there's no way to say in the grammar itself that if you have an identifier, in order for us to treat it as a variable, there has to have been a previous declaration for that identifier. Instead, what we do is that we use a context-free grammar, and we have things like symbol tables. And so what we do is that, okay, when the parser encounters an identifier in an expression, it's going to look in the symbol table to see whether or not it had been declared to be a variable. See, the grammar itself will not allow the parser to do that. And so that's what we do. Okay, we use context-sensitive grammar because they're relatively straightforward for us to use, and then we have to augment that with other things like having a symbol table. Okay. All right. So now you know a little bit about grammars. Okay, the hierarchy of them. I mean, we could have used context-free language to define all our tokens. Okay, but it turns out that we could have done that with regular grammar. A regular grammar is simpler than a context-free grammar. So, you know, why don't we use the simpler grammar for tokens, and then we then try to define the grammar for statements, then we'll use context-free and well, not try to use context-sensitive, okay? There's actually yet another bigger circle out here, which I don't even want to mention. So, okay, so this is a little bit of language theory. I think on Tuesday, I may talk a little bit more about where all this theory comes from, and you know, because you know, if you're going to write a compiler, well, Antler, for instance, Antler is a very sophisticated tool that knows how to, you know, given a grammar, it generates the parser and the scanner for you. Okay, well, in order for it to know how to do that, it's making use of quite a bit of language theory that's backing up all of this technology. And I think more traditional compiler classes will go more into the theory, and I've tried very hard to avoid doing that because in my class, I want the emphasis to be on learning how to use a tool like Antler and actually writing a compiler instead of getting your head filled with language theory. Now, if you go on to a graduate class in compiler writing, then for sure, you're going to learn more about the theory and some of the other topics that I've kind of, lightly brushed over, such as optimization, instruction scheduling, register allocation, whether or not a variable is live. All that is going to be part of the more theoretical aspects of compiler design. Okay, but in one semester, I just didn't think it would be practical for me to try to cover all that. Okay. All right, so now I know a little bit something about grammars. Okay. And see. Okay, parsers. Okay. Now we did talk about top-down parsers. In fact, top-down recursive descent parser. Before, at the very beginning of the semester, before we started using Antler and we kind of hand wrote a parser, I said this is an example of a top-down parser because you start out with the topmost rule of your language, which mostly is program, okay? And then you work your way down recursively, okay? And for example, when you're parsing a program, well, a program's made up of declarations and a compound statement. And a compound statement is made up of statements, and a statement could be an if statement. And the if statement is made up of more statements and a Boolean expression, and so forth and so on. Okay, so that's called top down. You start at the top and you work your way down, and it's often recursive because when you're parsing an if statement, you end up parsing the true statement and the false statement. And so there's lots of recursion going on. Okay, so that's why it's called top-down recursive descent. Okay, and yes, we wrote one of those by hand, and it turns out that that's what Antler generates. So when Antler reads your .g file and it generates a parser, well, that parser is a top-down recursive descent parser. Okay? And if you try to read the code that Antler has generated, yes, even though it's in C++, it's not the easiest code to read. It is top-down recursive descent. Okay. Now, the advantages of top-down recursive descent is that they are relatively easy to understand, right? I'm sure that you all have a basic understanding of how the parser works. Okay. But they are big and slow, and as you know, from when we hand wrote the parser in the beginning, you end up writing a little parsing. You write a little parsing function for just about every construct in the language. Okay. If statement has an if statement parser. A while loop. Oh, there's a while statement parser. There's a expression parser. Expression parser. Well, that's made up of a simple expression parser, a factor parser, etc., etc. So you end up with lots and lots and lots of these little parsing functions. And then they end up calling each other a lot, right? It's top-down recursive descent. So, statement parser calls the if statement parser. If statement parser calls the expression parser. Okay? So calling functions at runtime, there's a bit of overhead. And so you have lots and lots of these little parsing functions that makes your parser big. And it's slow because at runtime, all these little functions are calling each other. Okay, so big and slow. All right. Okay, so you, as I said, you end up writing a parse method for just about every individual production of grammar rule. And now the parse method, each parse function, okay, it knows the grammar, right? The parser knows the grammar of the language, and therefore if the parser is parsing an if statement, it's expecting certain things. I mean, it expects to see the reserved word if. Okay, it expects that after the if, there ought to be a Boolean expression. After the expression, there ought to be a then. Okay, so the parser is constantly expecting certain things in the source, and if it doesn't see what it's expecting, then of course that's a syntax error. Okay, so so each parse function calls other parse functions, et cetera, and the parse functions, of course, are consuming tokens. Remember, I said that after the parser has seen a token and knows what to do with that token, it has to move on to the next token. Okay? And if it fails to do that, then your parser goes into an infinite loop, being stuck on the same token over and over again. Okay? So this is what's going on, as you know. Okay. Now, maybe because we're using a parser that Antler generated for us, we may have kind of forgotten exactly what's going on. But yeah, this is what's going on. Okay. All right. Now, a parse is considered successful if we're able to derive the input string, in other words, the source program, from the production rules. Okay. And so in other words, if you're given a program, okay, in our case, a Pascal program, from the grammar rules of Pascal, can you derive that program? So in other words, can you go through each rule and say, okay, well, this rule produces this string, and et cetera, et cetera. Will you end up with the source program? And if so, then you know that that is a legitimate program according to the grammar rules. It doesn't have syntax errors and so forth. Okay, and then of course, when the parser is working on your program, it has to consume all the tokens, right? There ought not to be any leftover tokens and so forth. Okay, so that's how top-down parsers work, and that's how we know that it succeeds. Okay. All right. Well, if they're top-down parsers, then of course there are bottom-up parsers. Okay. Now, a very popular form of bottom-up parser is a shift-reduce parser. Okay, and as the name implies, okay, instead of starting with the topmost rule in the grammar, okay, what the shift-reduce parser does is it starts with the tokens, and it tries to work its way up to the topmost rule. Okay, so a bottom-up parser will then look at the tokens of your source program. So the scanner has already produced the tokens, and then it tries to put the tokens together to match the rules of the grammar, and it then works its way up to the top grammar. And if it reaches the top rule, which in our case is program, then the parse was successful. Okay, so it's bottom up. Okay. Now I'm going to show you a bottom up parser and show you how it works. Okay, I'm not going to show you how to implement one, but I'll show you how it works. It uses a stack, so it's a parse stack. Okay. Now already you've seen a lot of stacks being used. Remember, there's a symbol table stack, and there's a runtime stack, and so forth. Well, to use a bottom-up parser, the parser itself uses a stack called the parse stack, okay, which starts out empty. Okay, now it's called shift reduce because pushing things onto the parse stack is called shifting. Okay, so the parser shifts input tokens, okay, which are terminal symbols, from the source program onto the parse stack. Okay, and so that's the shifting part. Okay, now when what's on top of the parse stack, okay, matches the longest right-hand side rule, grammar rule, then the parser pops off those matching symbols and reduces them to the non-terminal symbol on the left-hand side of the rule. Okay, so that's the reduction the reducing. Okay, so again, you're shifting tokens from the source program onto the parse stack. Okay, when the tokens at the top of the stack, not the entire stack, just the tokens at the top of the stack, the few tokens at the top of the stack, if they match the right-hand side of a grammar rule, then you pop off those matching tokens and you replace them with the left-hand side of the grammar rule. And the left-hand side being, a non-terminal symbol. Okay, and so that's the reduction. Okay, and so you keep doing this shift, reduce, shift, reduce, shift, reduce until all that's left on top of the parse stack is the topmost grammar symbol, which in our case is program. And then you know that you're done. Okay. Well, that's certainly a very different approach to parsing. Okay. And so, okay, well, here's an example. Okay, so here's a grammar rule. Okay, we're still using a context-free grammar. Okay, but here's a rule. A term is a factor times a factor. Okay, so let's say that during this bottom-up parsing, on top of the parse stack, we have a factor, a times, and a factor. And at that point, we pop off those three items, factor, star, factor, from the top of the parse stack, and then push in replacement term. Okay, and that's a reduction. Okay, and so you just keep doing this until all that's on top of the stack is program, and then you're done. Okay. All right. So then we can say that, oh, now the parser has accepted the input source as being syntactically correct. Okay. Fancy way of saying that the parser decided that that is a legitimate program. Okay. All right. Well, let's take a look at this, and then I'll point out why this is an attractive way of doing parsing. Okay. So so here's simple grammar. Okay, and in this case, the topmost rule is expression. Okay, so expression is a simple expression. A simple expression is term plus term. A term is either a factor by itself or factor times factor. A factor is a variable is an identifier, and an identifier is either A, B, or C. Okay, very, very simple little grammar. And this is the input. Okay, and we're going to use a shift reduce parser to parse this expression. Okay. All right. Well, here's our a little table that keeps track of everything. Okay. So in the first column will be the current state of the parse stack, where the top of the stack is at the right end. Okay. So here we go. Okay. So here's the input. Okay. And first thing we do is a shift. Okay. And so now A is sitting on top of the parse stack. Okay. And next thing we do is whoa, look, A matches the right-hand side of a rule. Okay, so we do a reduction. Okay, and so A is popped off, and we replace it with identifier. Okay, oh look, identifier matches the right-hand side of a rule, so we do another reduction, and identifier then becomes variable. Okay, oh, variable matches the right-hand side of a rule, and so we do another reduction and reduce variable to factor. Okay. All right. Are we okay so far? All right. Well, factor. Oh, look, factor does match the right-hand side, so factor is reduced to term. Okay. Now, term by itself doesn't match anything on the right-hand side, and so we do another shift. Okay. So shift, and now on top of the stack we have term plus. Okay. Well, term plus doesn't match anything on the right-hand side, so we do another shift, okay? And now term plus B, okay? All right, well, here we go again. B matches the right-hand side, and so B is reduced to identifier. Identifier is reduced to variable, okay? Variable is reduced to factor. Okay. All right, now at this point, let's see what happens. Okay. Well, we actually do a shift. Okay. And why is it a shift? It's because yes, factor does match here, and we could have reduced it to term, but remember, we're trying to match the longest possible right-hand rule, and because the next input character is a star, we're going to try to match this rule. Okay, so then we do a shift. Okay, all right, so we do a shift. Okay, and so then the star goes to the top of the stack. Okay, well, well, none of this matches a right-hand side of the rule, so we do yet another shift. Okay, so shift. Okay. Okay, well, here we go again. Here's C matches identifier, and so reduce C to identifier, reduce identifier to variable, reduce variable to factor, and lo and behold, now we're matching factor times factor. So when I reduce factor times factor to term, okay, term plus term, oh look, it matches this rule. So we reduce term plus term to simple expression. Okay. Simple expression matches the right-hand side of this rule. So we reduce it to expression, and expression being the topmost rule means that we have succeeded, and we do an accept. Okay. All right, so you're looking at this and thinking, oh my God, why would anybody want to parse this way? Okay. Well, it turns out that all these shift and reduce actions, okay, all of this could be table driven. Okay, we could have had a table that tells us, should we now do a shift or should we now do a reduce? Remember how we wrote that table driven scanner and how much smaller that scanner was and how much faster it was because everything the scanner did was driven by this table. Okay. Same thing with shift reduce parsing. All of this could have been driven by a table. And just like with the table driven scanner, that's going to make the parser blazingly fast because every time it is in a certain, when the parse stack is in any state, the table will tell it, okay, and the table entry and the next input character together will say, okay, now you should do a shift or now you should do a reduce. Okay. Now, just as with the table-driven scanner, that table is really hard to create. Remember, we have to draw this elaborate state transition diagram, and from that diagram, we then could then generate the state transition matrix, and it was that matrix that was our table to do the scanning. Okay. Similar process here. In order to create that table, is by hand. It will be very, very difficult to do. Very hard to debug if there's a problem with that table. Okay? And so you don't want to create this parsing table by hand, but then you would use a tool, to read in the grammar and have that tool generate the table. And then therefore that tool can then generate a bottom-up shift reduce parser that's going to be a lot faster and a lot smaller than a top-down recursive descent parser. Okay? Now you know that Antler generates a top-down parser. Okay? There are other tools that will generate a bottom-up parser and it will create that table. Okay? All right, well, okay, as I said, everything can be done with a table. The parser becomes much smaller and much faster. Okay, I can tell you pretty reliably that the C++ compiler uses a bottom-up parser. Otherwise, your compilations will take even longer. Okay. All right, so if your grammar gets, any grammar that's of a significant size, it will be very difficult for you to generate this table by hand, and certainly to try to debug this table will be extremely difficult. Okay. Now, remember, I did tell you that a sign of a good compiler is how well it handles syntax errors, right? People write programs, people make syntax errors, and you want the compiler to first of all, flag the errors and put out a meaningful error message. Okay, that's not the easiest thing to do with a top-down parser, and it's not easy to do with a bottom-up parser. And you know that the C++ compiler is known to generate cryptic error messages. Like, you do something simple like have unbalanced parentheses. And instead of saying, hey, you're missing a white parenthesis, it's going to say something really cryptic and maybe give you half a page of error messages. Okay, so you know that the C++ compiler has a hard time giving meaningful. It has a hard time doing meaningful syntax error handling, and hopefully any compiler that you write will be better. Okay, but I think bottom-up parsers is even more of a challenge, because at least with a top-down parser, I think each of the parsing functions kind of knows where it is and knows what to expect. So for example, the if statement parsing function can say something meaningful like, oh, look, you're missing a then, or you're missing the else. Okay? Whereas the bottom up, well, depending on how the parser was generated, it may not know exactly where it is. And so it then spits out some generic error message that may or may not make sense. Okay? So either case, syntax error handling is a challenge. Debugging the compiler, the parser will be a challenge. If something goes wrong, like, gosh, the parser didn't parse this statement. It keeps claiming there's a syntax error in my statement, and there really is no syntax error. Well, it could be a bug in the parser. Most likely it's a bug in your grammar, that you didn't specify that rule properly. The parser was generated correctly, but because the grammar rule was wrong, then the parser isn't doing what you expect. Okay, so if you're writing a compiler and it's not parsing a statement correctly, check the grammar before you blame the parser. Okay. All right, I'm going to close the door here. So gardener next door is making lots of noise. Thursday in my neighborhood is mow and blow day, and so you hear all these really loud leaf blowers. Okay, so I want to introduce you to Lex and Yak. Okay, Lex and Yak were one of the early compiler writing tools. Came out, I guess, in the late 70s or early 80s, and they're pretty much standard. If you have a Unix operating system, Lex and Yak will be there. If you have a Linux system, either you'll have Yak and Lex, or the GNU versions. Instead of Lex, it's called Flex. Instead of Yak, it's called Bison. But yeah, they do the same thing. They just renamed them and rewrote them. Okay. So Yak stands for yet another compiler. In the 60s and 70s, people started realizing that writing compilers was a real pain. Yeah, they're large programs, very difficult to write. And so people started doing a lot of research into compiler writing tools. And so there was a whole slew of them. And so that's why Yak is called yet another compiler. I forget what ANTLR stands for, but it's somewhere along the similar lines, okay? So ANTLR is a very modern compiler writing tool, whereas Yak and Lex are considered the grandparents of today's tools, okay? Yak will generate a bottom-up parser written in C, whereas, as you know, ANTLR generates a top-down recursive parser written in either Java or C++. Yak will generate, give it a grammar, it will generate a bottom-up parser written in C. Okay, so let's take a look. Okay, now your ANTLR grammar file, your .g file, contain both the production rules of the statements of your language and the rules for the tokens, right? The tokens were at the bottom part of your .g file, okay? Yak and Lex separated them into two different files. So you have one file for what's that, .l file that contains the regular expressions that describe the tokens of the language. And then there's a .y file that contains the actual grammar rules. Okay, so here, this is the Lex file, okay? Token definitions, that's why it's a .l file. So this is going to be a grammar for a simple calculator, okay? So, all right, well, let's look down here, okay? This says that if we see a blank or a tab, okay, well, the action we want the scanner to take is to ignore it. And so it's basically an empty statement here, okay? If we see, if we see a number, okay, so this is a regular expression to describe a number. It says one or more repetitions of a 0 or 9, okay? Optionally followed by a star. So this backslash dot says, okay, a literal dot, and the question mark says optional, okay? That followed by 0 or more digits, okay, that's a star here, 0 or more, okay? Sorry, and this is or, okay, so here, okay, so the first version of a number is one or more digits optionally followed by a period or decimal point, or it could be 0 or more digits, okay, definitely followed by a period, followed by one or more digits on to the right of the decimal point. Okay, so this describes two different versions of a number. Okay, and so this is the or here. Okay, now what do we want the scanner to do when it encounters a string of digits and decimal point that matches the definition of a number? Okay, well, we want to scan it and basically read it in. Okay, so we're calling the C scan function to say, okay, read that string of characters, and okay, you see that the formatting is that it's going to be a float, okay, and store the value in YYL val, okay. YYL val is a predefined variable, okay. And then we want to tell the parser that what we got was a number. So we're saying, okay, what we saw was a number, okay. Now, if we instead saw just a carriage return or a line feed, okay, well, what do we want the scanner to do? Okay, well, there's going to be a line number, a variable, so we increment it. And what we're going to return to the parser is that, hey, what we saw was the line feed character. So we're just going to return that character, okay? Now, dot here, okay, when it's not a literal dot, which would be backslash dot, when it's a dot, okay, that's a meta character, that represents any other character. So if it's not a digit or a decimal point or a blank or a tab or a line feed, then any other character, we're just going to return it. Okay? And so YY text is another reserved identifier, and it will contain the string that the parser saw, and so we're just going to return the first character. Okay, so that's okay. So this is the Lex file, and from this description, now see our grammar, our language is very simple. It just has numbers in it. Okay, so based on this Lex file, the Lex will then generate a table-driven scanner. Okay. All right. Well, then here is the YAC file. Okay, it has all the production rules. Okay, and you notice that. Okay, here are the tokens. Okay, token number. Okay, which is one of the things that the scanner could return. Okay, and all right. So and then other tokens are plus sign, minus sign, star, and slash. Okay, now the order that we listed these tokens will then determine precedence. Okay, so lowest precedence will be plus or minus, and the higher precedence will be star and slash. Okay. All right. Well, here are the grammar rules. Okay, and it says that an expression list can be empty, or it can be an expression list followed by a line feed character. Okay. Or it can be an expression list followed by an expression followed by a line feed character. So you can see there's a recursion going on here. Okay. Now, if we see this rule, okay, well, we want this to happen. We want to basically print out the value of the second element of the rule. Well, this is the first element, this is the second element, and so we're basically saying that we want to print out the value of the expression. Okay, so what we're actually doing here is writing an interpreter for expressions. Okay, and so when the parser recognizes expression here, which is the second element of this rule, that's what the $2 stands for, we're going to print out its value. Okay. All right, well, what's an expression? Okay, an expression is just a number. Okay. Now, $$ says this is what we want to return as the value of recognizing. And so if the parser recognizes a number by itself, okay, well, we want to return the value of that number, and that's $1 because it's the first and only element of this rule. So that's what we return. So $$ is the return value. Okay. Now, if it's expression plus expression, well, what do we want to return? We want to return the value of the first expression, okay, or the value of the first element of the rule, which is this expression, plus the value of the third element, which is going to be the second expression. Okay, and then similarly all the way down. Okay. Now, if we encounter a parenthesized expression, then we want to just return the value of the expression, which is the second element of the rule. So it's $2. Okay. All right. So what's going on here? Okay, that the parser is recognizing. Okay, is matching is the protection rules to the input, and because we're writing an interpreter, here are the actions that we want the parser to take. Okay, so here for expression, we want the parser just to return the value of each of the expressions here, and then in expression list, which is a list of expressions, one or more expressions separated by line feed. For each expression, then we want to print out the value of the expression. Okay, so this is the YAC file. Okay, and basically it's a combination of parsing and actually executing the expressions. Okay. Wait. Yeah, just similar to the interpreter that we wrote, right? The parser built the parse tree, and then we walked the parse tree to execute the statements. Here, there's no parse tree. We're telling the parser to directly execute and evaluate the expressions. Okay. All right, well, so now we have our two files, okay? And now we need a main program. Okay, and here's the main program. All right, so YY parse. Okay, that is a predefined function when you get YAC and LEX that says, okay, tell the parser to do its thing. Okay, and then in our case, the parser will parse and execute the expressions. Okay? So there's the main program. Okay, main program, I've got it. So calc.y contains the grammar rules. Okay, and then I also included the main program in calc.y. Okay. Okay, so there are a couple of other things. Okay, there's YY error. Okay, so when the parser finds a syntax error or detects a syntax error, it's going to call YY error, and then you have to write what you want YY error to do. And so here I wrote YY error. This is the signature of YY error, and I just want to print out a warning message. Okay, so very simple. Okay, all right. Well, now that we have everything, here's how we built the compiler. Okay, so we have calc.y and calc.l. Right, and calc.l described the tokens. Calc.y had the main program and the production rules. Okay, so we're gonna call yak. Okay, I forget what the -d option means, but basically you're calling yak and you're passing in calc.y, and so okay, so that goes into yak, and then yak will generate these two files. Okay, y.tab.h and y.tab.c. Tab, as you might guess, stands for table. Remember, it's a table-driven parser. Okay. Then we call lex using calc.l, and lex will then generate lex.yy.c. Okay. All right. So now we have .c files from .h files, and so of course we then feed those into the C compiler. Okay, and then that generates our calculator program. Okay, all right. Well, let's see all this in action. Okay, so you're seeing something that's probably 40 years old that we're using, but this is not the very first compiler development tool, but probably the most popular one of its day, and I suspect these tools are still being used today. Okay, but then we have more modern tools like Antler. Okay, all right. So let's actually do this. Okay, so I want you to see the files being generated. So I had that here. There's yak. Okay, so in my yak directory, okay, hopefully you can see this. I have calc.l and calc.y. Those two files that I showed you earlier. Okay. And then I'm going to actually run these commands. Okay, let's see. Okay, let's actually open up the terminal window in this directory. Folder. Okay, so let's do. Okay, let's do calc.y. So there's the grammar that I just showed you. Okay, there are the rules, and then there's the main program, and then there's YY error, and here's the helper function. So I'm going to then do this command here. Okay, yak -d calc.y. Okay. -d y. Okay, and you'll see. Oh, okay, there's y tab.h and y tab.c. They got generated. Okay, and then I'm going to do lex of calc.l. Okay, well, here, let me show you calc.l. L is basically the rules that define our tokens. Okay, so here we go. Lex of whoops. Can't type calc.l. Okay, and that's going to generate. There it is. Lex.yy.c. Okay, there it is. Okay. Okay, lex.yy.c. Now I'm going to run the C compiler and everything. And so let's do that. Okay. What happened to my terminal window? That happens too often. Okay, there it is. Okay, so CC. I'm going to call the I'm going to call it calc. And am I compiling all the .c files? Okay. And okay, got lots of warnings because this is it's generating a very old version of C code, and the modern compilers give you lots of warnings. But here's calc. Okay. All right. Well, that means we now have a working interpreter for our expressions. So let's see it work. Okay. Slash calc. Okay. Let's give it something easy first. 2 plus 3. Okay. 5. Yes. We can say 2 plus 3 times 4. Okay, to make sure it got the precedence right. And okay, yes, it knew to do the 3 times 4 first. Okay, and we can do parentheses. 2 plus 3 times 4, and it knows, okay, we're going to do the parenthesized expression first. And this is all based on our grammar here that you saw. Let's see. Okay. Sorry. Where is that grammar? Just Lex file. And, okay, here we go. So these are the expressions. And here are the precedence rules, okay, that we always, plus and minus have lower precedence than multiply and divide, okay? And we have parenthesized expressions, and because of recursion, we should be able to have multiply nested, okay? So let's do 7 minus 3 times 4, okay, 4, and that should work. Okay, and sure enough, we got minus 13. Okay. Okay, now let's see what happens if we have a syntax error. So how about 2 plus 3, and I'm going to forget the closing parentheses. How's that? Okay. It says, oh, you got a syntax error. Okay, and so the parser that was generated by Yak and Lex do have rudimentary syntax error handling, and you can see that it then just killed your program. So if you want better error handling, then you got to do something else. Okay. Well, actually, what happened was that it called. It went ahead and called the YY error. Okay. What am I looking for here? Oops. Wrong class. 152. Okay. Okay, so it called YY error, and yeah, I just did a return. So I could have done something more meaningful here. Okay. All right, so now you've seen Yak and Lex, and have I ever taught using Yak and Lex? I know I've used Yak and Lex in my career. I've written several dozen compilers in my life, and some really simple ones, and some really compilers for full-fledged languages. And I'm trying to think. Yes, I have used Yak and Lex early on, but then it made much more sense to use more modern tools. Okay, but there's Yak and Lex, and now you can claim that you've seen Yak and Lex in action, and by golly, if you really like it, there are all kinds of tutorials online, and you can learn all about these two tools, and so you've gotten a very simple introduction to them. Okay? All right, any questions at all about what we covered today? Okay, so you got a little bit of language theory. You learned about different classifications of grammars. Okay, we use regular expressions to describe our tokens, and we use context-free grammar to describe the production rules for the statements of our language. We saw that context sensitive is more powerful, but too difficult to use. Okay? So we use context free and use things like symbol tables to augment the grammar, and so that our parser will know what to do. Okay. Then I showed you, well, we talked about top-down parsers that you've been using all along. Then I showed you a bottom-up parser. I showed you a shift reduce, okay, and pointed out that all these shifting and reducing operations can be table-driven, and the table is going to be driven by the table will be generated by a tool like a Yak and Lex. Okay, you don't want to create this table by hand. In fact, why don't we take a quick look at what was generated, and you'll get an idea of what it looks like. Okay, so you can come back here, and okay, let's take a look at okay, what did Lex generate? It generated lex.yy.c, and let's see what it looks like. Okay, it's going to be C code. Okay, all right, there it is. Okay, and no claim that it's readable, but here it is. Okay, and so let's see if we can find the table in here. Somewhere in here, there's going to be a table. So even for a very simple, okay, here we're starting to see tables. Okay, now you know these tables tend to be very sparse, and so instead of having one gigantic sparse table, what Lex did was generate parts of the table, and that's so you can see bits and pieces of this table that it's using to do the scanning. And then here's the code that's actually running everything. And it is all in C, and quite difficult for us humans to read. Okay, now let's take a look at what Yak generated. It generated ytab.h. So let's see what's in ytab.h. Okay, oops, sorry. Ytab.h. Come on, what's going on here? Something is running in the background of my machine that's just eating up everything, and I need to find out what it is because it's driving me nuts all day. Oh, good grief, I don't know. Oh, good heavens, look what it did. Okay, anyway, here is ytab. Jeez, ytab.h. All right, well, okay, here's number. Okay, so number is actually an integer that is using, oh yeah, here's number, it's 258. A lot of this is just a comment, but the guts of the parser is, wow, the machine is really going crazy here. I can hear my fan going like crazy, so something has started up in the background. Oh, look at this activity monitor. Okay, as soon as class is over, I'm gonna have to find out what it is that's running. Okay, let's see if I can get back to where I was. Wow, see how slow the machine is? Okay, so, okay, there's Yak. All right, so let's see what ytab.c is. Okay, well, tab, you can guess, is table. So let's see. Drag it in there, open that up. Okay, there's one. Okay, let's close that one. There's ytab.c. Okay, let's see if we can see a table in here somewhere. Oh, yeah, okay. Now you're starting to see bits and pieces of a parse table, okay? And even with a very simple grammar, there's quite a bit of it, okay? Yeah, you can see the code has a lot of macros in it, pound defines, okay? So it's not going to be the easiest code to read, but it is generating parser written in C. Okay? All right, I hope this was interesting. And you're lucky that we're not using this tool because really Antler is much nicer to use. And Antler generates parse trees. We can print out the parse tree. You know, Antler grammar can generate syntax diagrams, and so all kinds of more modern features that we can take advantage of. Okay, whereas Yak and Lex are very primitive. Okay. All right. Any questions at all? Okay.
Professor, do we need like slides for the presentation?
Do we need to add what?
Slides. Do we need like?
Yeah. It's up to you. If you think you want to have some PowerPoint slides, maybe as an introduction, you know, list some bullet points about what's cool about your language, and you know, if you want to show syntax diagrams, well, either you can generate them right in front of us, or have them already pre-generated and pasted into some slides. Yeah, it's up to you how you want to present.
Okay, thank you.
I would say that the majority of the presentations that I've had in the past did have some PowerPoint slides, or whatever slides you want to make. Okay, it's probably best to have some things set up ahead of time, because you know, you only have 10 minutes, and if you try to do it live, if things go wrong, then that's going to eat up a lot of your time. Okay. Any other questions? Okay. All right. Well, I hope. Let's see. I forget. Let's see. Hang on. Where are we? Assignment 6. Okay. So okay. Well, assignment 6. You turned that in already. Make sure the grader is working on it, and then yeah, you should all be busily working on your compiler projects. And you know, in all the years I taught this class, I started teaching this in, I guess it was fall of 2008. So I've been teaching this class for quite a while. I started out in the computer science department, and then I ended up teaching it in both departments. I'd say only a handful of teams have completely failed to produce a compiler. I mean, if you can, even if it's working for just a very tiny subset of your language, if you can write a simple program, have it, your compiler compile it to Jasmine, assemble the Jasmine and run it, I would say that you should at least do that. Okay, I want to see something working with your compiler. Okay? Even if it's just, you know, a few assignment statements and a print statement and maybe an if statement. I mean, get something working. I would say that that's still an achievement, because you know, compilers are not the easiest programs to write. And I'm sure that at the beginning of the semester, when I said that you're going to be writing a compiler, that was probably kind of scary. Okay, but you're so close to actually doing it now. Okay. All right. If there are no more questions, then I will have my office hour in about 15 minutes. If you want to stop by and we can chat, and we can do that. Okay. All right. Okay. Let me see another message that popped up. Let me check and make sure it's not for me. Okay. It's all right. Stopping sharing. Thank you for coming. We'll see you on Tuesday.
Thank you, Professor.
You're welcome.